So we were outside collecting some data about how many moves it takes to play this game with various numbers of players. So while we were still inside, we played the game with just 2 players. Okay, so when we had 1 pair or 2 people, it took how many moves? 3. This isn't turning on. Okay, it took 3 moves. And then we went outside and we started playing with 4 people, right? 2 on each side of the center stone. And how many moves did it take to move everyone to the other side? 8. Okay, so how about when we played with 3 and 3? Total of 6 people. 15. And then we were working on 4 and 4. Both groups got it, but only one group remembered to count while we were doing it. And so the group that counted, what did we get? 24. Good. Okay, so that's as far as we got to try out, live and in person. And it got harder and harder as we added more people. So we might not even want to try with 5 and 5. Maybe it's just too hard, right? So maybe we could look at what we have and try to predict how many are going to be how many moves it would take for 5 and 5. Chris, you think 35? Anybody have a different guess? 35? Greg, was that your guess? Yeah. Greg, right? What's the pattern? What do you see? Here, plus 5, plus 7, plus 9, plus 11. So if I do plus 13, I would get 48. Good. Good. So that's great. We saw a pattern, and it looks like the pattern is we're adding odd numbers, right? You add the next odd number to the previous number of moves. So if I want to predict the number of moves for 7 pairs, right? So T sub 7, right? That would be the next one would be plus 15. 48 plus 15 is 63? 63. All right. So now I want to write a formula, right? I can use recursive or explicit. Recursive is usually easier. So I think I'll try to do a recursive formula where I explain this pattern using our new notation, right? So we all can see the pattern. So all I have to do now is translate it, right? So that's the hard thing to do. So I'm going to write in English what pattern we see. So I would say each number in the sequence is the previous number plus something, right? The previous number plus what? What am I adding to the previous number of moves? Ooh, that's what I'm adding to the last thing I added. But like to get from 3 to 8, I added 5, right? So I did to get the 8, I took the previous number and I added 5, right? And then to get the 15, I started with the 8, the previous number, and I added 7. And to get the 24, I started with the previous number of 15 and I added 9. So you're not always adding the same thing, right? So to say 2 would be wrong because you would be, if I was just adding 2 every time, it would be 3, 5, 7, 9, 11, right? So I'm not adding 2 every time. What I'm adding is increasing by 2. Odd numbers increase by 2. Yep. Those are all the odd numbers. So I'm taking the previous number of moves and I'm adding an odd number, right? So and let's say appropriate odd number. So figuring out how to express which odd number to add is really the tricky part of this problem. So let's translate the beginning part first, though. Each number, I'll translate that to t sub n. Right? So any generic number in the list is equal to the previous number. So that's the is, right? Equals the previous number. How do I denote the previous number using our new notation? T sub n minus 1 plus, then I have to add some odd number. Okay? And that odd number is changing. It's not just the same number all the time. It's an odd number, but it's a different odd number every time. So I have to come up with some sort of like mathematical way of writing an odd number. So maybe I can use my n's to help me. Right? So maybe my n could help me generate the number I'm adding. So when n is 2, the number I'm adding is 5. So I'm trying to look at a relationship between the n value and the number I'm adding. Okay, when n is 3, the number I add is 7. When n is 4, the number I add is 9. One more than what? One more than n? One more than 2n, right. Okay, so when n is 2, 2n is 4, and I add 5, right, which is one more than double the number. So when n is 3, 2n is 6, and what I add is 7, one more. Okay, so I'm always adding one more than 2n. Right, this is my list of 2n's. The number I add is one bigger than it. So I'm going to add 2n plus 1. So that is the last piece of my formula, plus 2n plus 1. There's a recursive formula. The explicit formula is much trickier for this one. You definitely could try to play around and find a formula. I've had many students do it, but I wouldn't ask you to do something like this, like on a test, right? I wouldn't ask you to find an explicit formula that's really hard to figure out. But this, the recursive, wasn't so bad, right? But we did have to notice that the 2n's were related to the number that we were adding. All right. How do you feel about that? Kind of okay? All right, so there's a worksheet on the next page, and I forgot to make it an official part of your homework. So it doesn't say in the learning objectives area where I usually write your homework. Down here, homework. It just says my math lab, right? So I would like you to also do the sequences worksheet. Okay. So the worksheet, Intro to Sequences, I want you to do this for homework. Hand it in next week on Thursday. Yeah. So this is going to be due Thursday of next week, which is, the date would be the 31st. Yeah. All right, so now, basically, we spent a whole class learning notation, right? The language, how to translate from being able to see a pattern and talk about it in English to being able to talk about it sort of in math notation language. And the reason we did that is because we're going to use that language to study 3 different kinds of sequences before the next test. We're going to talk about population sequences, and then we're going to talk about the Fibonacci sequence in a couple of classes. So the first kind of sequence we're going to look at is a linear population sequence. So what is a population growth model? It's a way to describe how a population is growing. And the population, when I use the word population, it could represent anything: a population of humans, a population of rabbits, a population of dollars in a bank account, right? So it doesn't have to be animals, right? Just any population. It could be bacteria. So we're going to talk about population as a sequence of numbers. So for example, we could write the populations of Greenfield on January 1st of each of the last 20 years. And that's just a list of numbers, which is a sequence. So P sub 0 would be the size of the initial population. P sub 1 would be the size of the population after 1 unit of time has passed. P sub 2 is the size of the population after 2 units of time. So it's just a list of numbers. So what we're interested in is the transition rule, right? The recursive or the explicit rule that tells you what happens to the population at each time unit transition. So a linear growth model is a specific kind of model where we know the transition rule is always going to be that the population grows or shrinks by the same amount, the same absolute amount at each transition. So that the sequence results from linear growth is called an arithmetic sequence, and we learned that last class. When you always add the same amount to get from one term to the next, we call that an arithmetic sequence. And when an arithmetic sequence is used to represent population growth or decay, we call it linear. So for example, here's an example of linear growth. We have a nuclear reactor. It has a 100-ton tank for storing high-level radioactive waste. There are 35 tons of waste in the tank already, and the reactor generates 5 tons per year. So I want to write a recursive and an explicit formula for P sub n, and P sub n is going to represent the amount of waste in the tank, and n is representing year. And then we're going to determine how long it will take the tank to fill up. So first, let's make a little table. If I have n P sub n, right? When n is 0, how many tons are in the reactor at time 0? Read it again. 35. It can hold 100 tons, but there are 35 tons in it right now. So at time 0, we have 35 tons. Okay. So 1 year later, we gain 5 tons per year. So how much do we have 1 year later? 40. And 1 year after that, we have 45. 1 year after that, we have 50, etc. Right? So if I want to write a recursive and an explicit formula, so I'm going to write 2 different formulas that represent the exact same thing. Just one is going to use previous numbers in the list. So a recursive formula looks at the relationship between P sub n's, right? Which would be what? What's my relationship here? Plus 5. Yeah, plus 5, plus 5. So my recursive formula is going to say each number in the list, P sub n, is equal to the number before it plus 5. How do I denote the number before P sub n? P sub n minus 1. So P sub n is equal to the number right before it, which we write as P sub n minus 1 plus 5. This is the recursive formula. And it's called it's the recursive formula because I'm using a previous number from the list. I'm using the P sub n minus 1. It looks at the relationship between numbers in the P sub n row, right? It doesn't consider n. Generally, it doesn't consider n. All right, now if I want to write a explicit formula, the explicit formulas look at the relationship between n and P sub n, right? So I have to be able to calculate for explicit, I have to be able to calculate P sub n only knowing n. P sub n equals, yep, 35 plus 5n. Can you explain to everybody how you came up with that? Yeah. Very good. That was a really good explanation. So you start with 35, right? So we put P sub n is always going to be 35 plus something, right? Because we're starting with 35. And when n is 0, right, you add nothing. So we have so that kind of makes sense, because if you plug in a 0 for n, you just get the 35. And then you're going to add 5 every year for n years, right? And repeatedly adding 5 n times, we write as multiplication. 5, you add 5 n times, which is 5 times n. So you start with 35, add 5 every year for n years, and you get plus 5n. Okay, so the 5 in this problem is called the common difference, because 5 is the difference between the populations in any two successive years. So if we pick any two consecutive years, like year 1 and year 2, subtract the populations, 45 minus 40, you get 5. Right, so the difference between any two populations in a row is 5. We call 5 the common difference. Oh, I didn't finish the question, did I? I was also going to determine how long it takes to fill the tank. So this is my explicit formula. I should write that down. It's explicit because it only uses n, no other numbers in the P sub n list. All right, so I want to know how long it takes to fill the tank up. So I have until I reach 100 gallons. So how do I figure it out? I could definitely do trial and error. I could just continue this table until I hit 100 and see how many steps it took to get there. Yep, that's definitely a good way to do it. But if I had asked how long until I reach, 1,000 gallons, if I had a 1,000-gallon tank, this would be an awfully long table to fill out, right? Ryan, what do you think? Plug in the amount it takes. Uh-huh. Okay. Yeah, so I can use my explicit formula. I'm just continuing my work down here. P sub n is 35 plus 5n. Use my explicit formula. And they want to know how long or in what year. And n is representing years, right? So I'm going to be solving for n because that's what they asked me about. Until I hit 100 gallons. So P is representing the population size. So I replace P sub n with a 100. And I have 35 plus 5n. And I just want to solve this equation. So you guys remember how to solve a two-step equation from a previous math class? Subtract 35 from both sides, right? So this side they go away, and I have 5n. 100 minus 35 is 65, and then you divide both sides by 5. 5, and we get n equals 13. So after 13 years, we'll have filled the tank. Great, what'd you do?
I figured out that it was just, since it was 100 years, there's only 50 left, so I just took 5 divided by 10 and added to 30 there.
Nice, good. So Brittany started from knowing this, right? She said, well, in year 3 there's 50. That means I need 50 more gallons to fill the tank. So she said, okay, 50 more gallons to fill. Divide that 50 by 5 because you take 5, add 5 every year. So that means 10 more years to fill the tank after year 3. So she took the year 3 plus 10 more years, got the 13. Nice approach. So in some cases, you might be given different starting information. So that was a great segue, Brittany, right? Because you just took the starting information 3, 50, right, and extrapolated to the information you wanted to know. Sometimes you might not even be given the amount at time 0, right? So like in this example, I have P sub 3 is 28 and P sub 6 is 40, and that's the only information you get, other than this is linear. It grows by the same amount every year. So I want you to take those two pieces of information and try to write formulas, recursive and explicit. And I'll give you a little hint, a little place to start if you're stuck. 0, 1, 2, 3, 4, 5, 6. Make yourself a table like we did in the last example. Put in what you know. See if you can fill in the table from there. And once you have the table, then write your formulas. All right, let's discuss it. We'll go over these. So how can I fill in the rest of this table? I only have these two pieces of information. What do I do? Yeah, Greg. Great. So you said, okay, I increased from 28 to 40, right? Which is an increase of 12. And that happened over 1, 2, 3 years. I increased by 12 over 3 years. So that would be an average of 4 per year. So I'm going to add 4. 28 plus 4 is 32. 32 plus 4 is 36. And 36 plus 4 is 40. All right, so if my rule is add 4 each year, what has to happen in year, what has to be in year 2 so that when I add 4, I get 28? 24. Yeah, and so I subtract 4 to go backwards, add 4 to go forwards. So 24 minus 4 is 20, minus 4 is 16. So I get the whole table filled in now. And my common difference, what is my common difference? 4. So my recursive formula, P sub n, is going to be P sub n minus 1. Just take the previous number and add 4. And then my explicit formula, follow the same model that we did before. Take the starting amount of 16 and add 4 every year for n years, so 16 plus 4n. Great. So we've just done 2 problems where we've come up with formulas without me having given you any kind of a general rule for how to do it. We've just sort of used our common sense. But here are the actual rules, right? This is how you do linear growth. For a recursive rule, you should give the starting amount, right? And then the formula is always going to be P sub n equals P sub n minus 1 plus the common difference. That's going to be your recursive rule. And your explicit rule is always going to be P sub n is equal to your starting amount plus the common difference times n. So this is exactly what we just did. If you don't like to memorize things, you don't have to memorize these because we just came up with formulas without having known these to begin with. It's just written in words, exactly. Yep. But if you like to have formulas, you can refer to these if you want. All right, so let's move on a little bit. A manufacturer currently has on hand 387 widgets. And over the next 2 years, he wants to increase his inventory, right? So there are certain reasons that manufacturers might do this. Like sometimes you get a better price for your product at a certain time of year. So you might store all the things that you make and hold them until you can get a better price, right? So this manufacturer currently has 387. He wants to increase his inventory by 37 widgets a week over the next 2 years. We want to know how many widgets the manufacturer will have on hand after 20 weeks and n weeks. Okay, so if we make a little table, we could have n and w sub n for number of widgets, right? And at n equals 0, I have 387, right? And then at one week later, right, because n is going to represent weeks, 387 plus 37, I should get a calculator out here. 424, right? Next week, I have 424 plus 37, 461. That should be more than enough information to write my formulas. All right, so W sub n recursively, right, is going to be the number of widgets I had the week before, which is W sub n minus 1, plus how many? 37, yep. And my explicit formula would be what? Plus 37n, because n is number of weeks, right? So we have 387 widgets plus 37 widgets each week for n weeks. All right, so how can I figure out how many widgets I'll have after 20 weeks? I could plug in 20 for n. I could just extend this table until I hit 20, right? But that is tedious, yeah. So I could also just figure out, okay, well, W sub 20, right, the 20th number in my list, would be 387 plus 37 times 20. Just replace the n with a 20. Oops. So I have 37 times 20, and then add that to 387, and I get 1127 widgets in storage. And I actually answered part B before part A because I used the formula to answer for 20. So this is the recursive and the explicit formula for how many widgets there are after n weeks. So sometimes it might be handy to write the formula first, right? Some people prefer to do it after. Some people prefer to do it first. All right. How many weeks until the manufacturer has 720 widgets? How could I figure it out? For W sub n, yeah. W is representing the number of widgets. So here's my formula. I'm going to use the explicit formula because, what was this, 387 plus 37. And so the explicit formula, because I don't know anything, I only know the first 3 numbers in the list. So if I'm looking for when I get to 720, I don't know the number before that. So I can't use the explicit form, the recursive formula won't help me. So now they're asking me how many weeks, right? N is representing number of weeks, so I'm going to be solving for n, which means I'm going to replace the W with 720 widgets. And then I use my good old friend algebra, and I solve this equation. I could divide both sides by 37, but if I do that, I have to remember to divide both terms on the right by the 37. Yeah. That would be a less conventional way to approach it, which is fine. So I could also start by subtracting 387. Yeah. Yeah. So yeah, that is the more conventional way. Dividing by 37 first would also work. It's just you just have to divide both terms on the right by the 37. 333 equals 37n. Divide both sides by 37. What do you get? 9. 9 weeks. 9 weeks I will have 720 widgets. All right. So let's complicate this problem even just a little bit further. Okay. In a linear growth model, you add the same amount at each transition And the sequence that results is called an arithmetic sequence. So that's just to review what we've talked about so far. So moving on to number 10 here. Let's say that this widget manufacturer, he's trying to build up his inventory rather than put all these widgets on the market at once. And it costs $10 per week to store a widget. And he plans to store all of his widgets for the next 2 years. How much money is he going to be spending on storage? Okay, take the number of widgets times $10 times what? Times 52 for the number of weeks. Okay, so that's a really good thought. That's a good approach. You say, okay, well, each widget costs $10 per week. Multiply it by how many weeks we're going to store it for, which is actually 104 because it's 2 years. Yeah. But not every widget is going to be stored for the full 2 years, right? Because he's making them over the course of these 2 years also. How many widgets have to be stored for a full 2 years? No, because yeah, we started with 387. Those 387 are going to be in storage for a full 2 years. But then the next week, the widgets that he makes only have to be stored for 103 weeks, right? Because they weren't in storage for that past week. They were being made, right? And then the next 37, they only have to be stored for 102 weeks. How are we ever going to do this? This seems really difficult. Hire an accountant. I bet Excel would be really handy for figuring this problem out. But let's just write down what we're adding up. Right? Maybe we won't add it up just now, but we're just going to say, okay, well, I have 387 widgets that I start with. They are going to get charged $10 per week for 104 weeks. So I multiply those together. And that's how much money I'm going to spend just on my initial inventory of widgets. 387 times widgets times $10 a week times 104 weeks. All right, so that's how many are getting stored. That's the price for the widgets that are being stored for a full 2 years. Then I have to add to that all the widgets I'm going to make over 2 years. So the following week, I'm going to have 37 more widgets, right? Those 37 widgets are going to cost $10 a week to store. And how long are they going to be in storage? 103 weeks. Okay. And then the next week, I'm going to make 37 more widgets and move them to storage, right? 37 more widgets, $10 a week. How long are they going to be in storage? 102 weeks. Okay, and then I'll write maybe one more. 37 widgets the next week. Then they get moved to storage. And how long are they going to be in storage? 101 weeks. All right, I'm not going to write down every term. I'm putting a little dot, dot, dot. You get what the pattern is, right? And then finally, I'm going to have 37 widgets that are going to cost $10 a week to store for how many weeks? 1 week. Yeah. Say that again? Yeah. Ah, okay. Mm-hmm. So every term that I've written down here has 2 numbers in common, right? Except for this first term, which is 387. But every other term has a 37 times 10, right? Which is $370. Okay, so, and then that's how much you have to pay per week, so just the number of weeks changes. All right, so let's, I'm going to need some more room here. So 387, let's just figure out that initial output of cost for the original 387 widgets times 10 times 104 weeks. That's $402,480. So I've got 402, 480 plus. No, storage is actually very expensive. manufacturers sometimes have reasons to store their inventory, but more often they try not to overproduce because they don't want to pay for storage. Okay, so then my next one is 37 times 10, which is 370, right? So 370, why isn't this writing for me today? 370 times 103, right? Plus 370 times 102, plus 370 times 101, plus 370 times 1. So it's a little less messy, right? It's a little less ugly. I sort of can wrap my brain around what I'm trying to add up. It's how I'm going to add it is still unclear. So we have a fun little trick. I have 402,480. So that's just sort of, we'll add that at the end. The rest of this, I'm gonna have to come up with some kind of little trick to add these up. You use the formula, yeah. We're trying to develop the formula right now. Okay, so if I take this sum and I write it backwards and forwards, that's going to be my little trick. So I've written it forwards here. Now I'm going to write it backwards. So I'm going to put 370 times 1 plus 370 times 2 plus 370 times 3 plus the biggest one is 370 times 103, right? So I've written that sum forwards and backwards. So I'll keep this 402, 480 there. And then I'm going to take these two sums are equal, right? They add up to the same amount. You can add in any order you want. Does that make sense? They add up to the same amount. Okay. So this amount, this mystery amount is what I want to know, right? They add up to the same amount, but I want to know what is that amount. So both of these add to some mystery number we call x. Don't know what it is. But whether you add forwards, you add backwards, you get the same number. So here's my little magic trick. Take these two equations and add them together. What does x plus x equal? 2x. Good. And then add all my other terms together. So 402, 480 plus itself is 804, 960. Okay, so 300, right now I have 103 370s, and I want to add one more 370. So how many 370s do I have? 104, right? So because multiplication is repeated addition, and you can read this as 370 plus itself 103 times. And now I have one more 370, so I have 370 times 104. That's what I get when I add those two terms. Plus. Here I have 102 370s plus two more 370s. How many 370s do I have now? 104. 370 times 104. Plus. Here I have 101 370s plus three 370s. How many 370s do I have? 104. Plus dot, 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 plus 1 370 plus 103 370s, 104 370s. Okay. Now I just want to know what x is, right? I have 2x is equal to this great big sum. But if I just look at this piece of the sum, every term is the same, right? This is the same number added to itself how many times? 104. No. 103. Yeah, 103 times. If you look at these numbers here, I have 1, 2, 3, up to 103 terms. So I have 370 times 104 added, that number is added to itself 103 times. And I still have my 804960 equals 2x. Now I can solve for x. I can use my calculator to get the rest of these numbers, and I don't have to add up, type in, 103 terms. So I have 370 times 104 times 103 plus 804960, 4,768,400. That is double the number that I'm going to spend. That equals 2x. So I just divide both sides by 2. And I get $2,384,200. That's how much money the manufacturer is going to have to spend on storing his widgets. Whew. This 103 right here. This 103 represents, yes, the number of weeks that we're going to be storing the newly produced widgets. Because the exactly. Yep. Yep.
Another way we could do it, instead of like going through that whole rigmarole up there, we just take the 370 times 104 and just automatically go one number forward.
Yes. And that is where the formula is. This 104 is the number of weeks I'm storing, right? So that could be, that's like n, number of weeks you're storing. 103 is one smaller than that, n minus 1. So this is how the formula works. Let's go back to the arithmetic sum formula. Okay. If you're trying to add a long list of numbers, and that long list of numbers happens to form an arithmetic sequence, where each number is increased by the same amount every time, to get the answer, you can just add the first term and the last term, and multiply the result by the number of terms, then divide by 2. So the first term and the last term, multiply by the number of terms, then divide by 2. So I had my first term, right, plus times the last term, add the first term and the last term, multiplied the result by the number of terms, which was 103, and then divide by 2. So let's do another example. Another example where we're going to use the formula. Yes, Yurka. Because the way the question was asked, it said the original 387 widgets will be stored for 104 weeks because they exist already. So they have to be stored for 2 full years. But the next 37 widgets has to only be stored for 103 weeks because they didn't exist for that first week, so they didn't have to be stored. And so I'm kind of separating this first term. I'm saying, okay, I'll just add that at the end because it doesn't follow the same pattern as all my other terms. And so I said, okay, just save this for the end, and I'm going to add up the rest of the numbers and then add it to this. All right, so let's think about this nuclear reactor again. It's currently storing 35 tons of waste and producing 5 tons per year. The town in which the nuclear reactor is located decides that they're going to charge a tax on the company that owns that reactor. And each year the town is going to charge the reactor $1,000 for each ton of waste that it is currently holding. So they're just going to go in, look at the meter on the reactor waste tank and go, oh, you're holding 20 tons, you owe us $20,000, right? So every year they go in, they see how much waste there is, and they have to pay $1,000 for every ton. All right, so assuming the tank isn't emptied, how much will the reactor pay the town over the next 5 years, starting this year? Okay, so this year they have 35 tons of waste, right? So how much taxes do they owe to the town? $35,000. Right? That's how much they have to pay this year. Next year, how many tons of waste are they going to have? They're going to have 40 tons of waste, and which means they're going to have to pay $40,000. Right? And then the following year, they're going to have 45 tons, which means they're going to have to pay the town $45,000. And then they're going to have to pay $50,000. And then they're going to have to pay $55,000. Question is, what does that add up to? So in this case, we could just type it all in the calculator because there's only 5 numbers, right, which isn't too bad. But let's just use our formula for practice, and we'll check by just adding it up and see if the formula works. So the formula says you're trying to add a long list of numbers. Well, this isn't that long, but it should work for a short list too. They form an arithmetic sequence because I'm adding 5,000 each year, always adding the same amount. So they do make an arithmetic sequence. To get this sum, it says just add the first term and the last term, right? So I'm just going to add 35,000 and 55,000. Add the first term and the last term. Multiply the result by the number of terms. How many numbers am I adding up? 5. And then divide by 2. That should be my sum x. Add the first term and the last term, multiply by the number of terms, then divide by 2. So I'll do this in my calculator, and then I'll actually just add it and see if they come out the same. 35,000 plus 55,000 is 90,000 times 5 divided by 2 is 225,000. Dollars, right? Over 5 years, that's how much they will be paying in taxes. So let's actually just add up the 5 numbers and make sure that it comes out to $225,000 so that we can trust this formula. So 35,000 plus 40,000 plus 45,000 plus 50,000 plus 55,000 is 225,000. So that's how you can add a long list of numbers quickly if they are related, where they increase by the same amount every time. All right, so now I'm going to have you work in your groups for the last 20 minutes or so on this little worksheet called A Case for Wind and Solar.